Okay, Namrata and I'm Adam Baker. This is my colleague Namrata. We're here to talk about improving search in Workday products using natural language processing. So Workday, in case you're not familiar, is a large enterprise resource management cloud company. We're best known for our human resources as an HCM, human capital management software, but we have a large variety of resource management applications, from planning to inventory, financials. We've been focused on talent recruiting, and what we're doing, trying to improve search for that. But search really spans most of our products, and it probably spans a lot of yours. And we're also going to talk about NLP for recommendation as well, which is going to span many of our products too. So I'm just going to go over a few of the problems that we're trying to solve that seem to be looking for an NLP solution. So one is that in many cases we have users who put in data for like a worker profile or a candidate profile, and their data is noisy. So they're going to have many abbreviations and misspellings, and you're going to have a lot of synonyms. For example, in our work, we tend to use the words word vectors and word embeddings to mean about the same thing. And so we should probably, most of the time, treat those as synonymous, even if there might be some tiny, subtle difference in the usage and meaning of the words. And some other things we might want to be able to do is classification. So we might want to be able to construct a taxonomy of terms in some domain. And an example of why you would want to do this to improve search in particular is if you're searching for data science. If you have candidate profiles, if you have that have something like deep learning or R, but don't have the word data science in it, then that's probably also a document that you might want to see. So we might want to include that. And then we also have recommendation, not only for search completion, like we could say if you're typing in deep, you get deep learning, but also for filling out, adding data to your profiles to a document. So if your document has NLP, you might want to also add machine learning. So the agenda for this talk, I'm going to talk about why we use word vectors. I'm going to explain how we train word vectors. And then Namrata is going to talk about the use cases in more detail about how we're using them to improve search and other Workday UI. And she's also going to cover our model evaluation, how we evaluate the quality of the word vectors for a variety of tasks. So I'm going to start with asking, why do we want word embeddings? Why do we think they might help us? And so one of the first things the word embed you will encounter if you look at word embedding literature is you'll see these analogic reasoning tasks where word vectors actually do pretty well. So Athens is the capital of Greece, Oslo is the capital of Norway, and you have this sort of vector math that you can do where you say Athens minus Greece plus Norway, and the closest vector in your vector set is often going to be Oslo if you have high quality vectors. So just to sort of give you a graphical intuition, if this is a vector for Athens and here's the vector for Greece, you can subtract the two by moving the vector for Greece, the tip of it, to the tip of the vector for Athens and traversing Greece backwards. And that gets you Athens minus Greece. This is pretty good geometric intuition. You can move the vector for Norway over to that endpoint, to the tip, and traverse it forward. And that gives you Athens minus Greece plus Norway is often going to be that's where Oslo lies in your vector space. And so the important thing there is it captures some semantics. We don't actually need to do these SAT exam tasks very often, but a vector representation that captures this information might help us to do a lot of other tasks too. So just knowing that it's capturing some information about cities and the countries that they live in or suggests it actually knows something about these words. And you could do this with syntax too. Dollars minus dollar plus mouse often will get you to mice. So it knows something about syntactic relationships and morphological relationships. So these will help you for a lot of natural language processing tasks because so similar terms will point in similar directions. So you can use just off-the-shelf cosine similarity, measure the cosine of the angle between two different vectors for an off-the-shelf similarity metric. You can then use that similarity metric to rate suggestions. So given an existing document, rate suggestions for structured fields to add to improve the document, structured metadata. You can find similar terms in a taxonomy. So when you will need to add a new term to a taxonomy, you can find the similar terms, and you're gonna probably want to add it in the neighborhood of those similar terms. You can cluster them to construct a folksonomy or to look for synonyms as a first step in looking for synonyms. And you also want to look at these instead of these are often a good place to start because they're very cheap to train relative to a lot of other approaches. You don't need any labeled data. I'm going to go over this in much more detail. And there are very efficient training algorithms that can scale to like massive corpuses. So we train our word vectors using FastText, a library put up by Facebook. So the steps for doing that, you need to get a corpus. We've experimented with nudes feeds, web scrapes, social media posts, Wikipedia. There's lots of different corpuses. And then there's a model task that it uses that I'm going to go into more depth, SkipGraham with negative sampling. And it makes predictions about the words it's going to see in a corpus, and you're going to minimize the difference between the model's predictions and the actual corpus itself. And then you're going to iterate between these steps while tuning the hyperparameters, oftentimes for the downstream tasks that you have. So I mentioned SkipGraham with negative sampling. This is a diagram of the SkipGraham model. For the SkipGraham model, if you're looking at a phrase like, if we're scanning through a corpus and we run into a sentence that has an NLP-backed recommendation system, it's going to go through each of the words in turn and consider that a focus word. So in this case, suppose we've gotten all the way to backed as a focus word. And the task it needs to do is to predict all the words that are in its context window. So the context window is a tunable parameter. And here this illustration is showing just a context window of 2. So that means it's going to have to predict the words that are either 1 or 2 away on either side of the word backed. And in particular, the negative sampling part is it's going to try to predict which words actually occur in its context window, in contrast with some noise that you're going to sample from the corpus. So to look at this in more detail, SkipGraham with negative sampling infers a set of what I'm labeling just canonical vectors, a set of canonical vectors for each word. And then a second set of vectors called the context vectors for the word that are actually discarded. The canonical vectors are the output for the algorithm for downstream tasks. The context words are discarded. And then it defines a probability for a word within a window, a putative word within a window, given a focus word. It's just a sigma of the dot product of the canonical vector for the focus word with the context vector for the window word. And sigma is just this familiar S-shaped curve that's going to map any real number into a probability. So the task then is for every focus word, you're going to maximize the probability that the model assigns to a context word which actually occurs in the context, and you're going to minimize the probability that the model assigns to any noise randomly sampled from the vocabulary occurring in the context of that focus word. So the most important parts to pull out of there is, one, this is actually a fairly simple model. It's computationally efficient. There's not a whole lot to do, so you can actually run it pretty fast on a large corpus. And there's a lot of underlying tricks to make it even faster in FastText that I'm not going to go into. But another thing to take away from this can be summarized by this nice quote by J.R. Frith: "You shall know a word by the company that it keeps." basically these vectors encode everything that the vectors, all the knowledge that the vectors encode are about the words that tend to surround it, the context that surrounds the word. So it's going to learn a lot about vectors. When vectors are very close to each other, that's telling you something about how easily one can substitute for another one in a typical context. And so this gives us you can think about hyperparameter. This gives us some intuition for hyperparameters. For instance, when you tune the context window, you're going to want to tune this towards your downstream task. So a narrow window will give you functional, very syntactic like vectors. So if your downstream task might be to do a part of speech tagger, this might be what you want. But for a lot of our NLP work, we want a wider window, because a wider window is going to capture much more of the topics, the types of topics that the word shows up in. It's going to capture like other words that happen to be in a sentence or document with that word, and not just like what's one or two away from it. Dimensionality, like the number of dimensions in your vector space, that is a parameter that you want to tune to the size of your corpus and maybe the rarity of the words that you want an understanding of. So as you have a larger set of data for all the words and phrases that you want to understand, you can scale up the dimensionality of your model. And then I should mention that one of the nice things about FastText is it has a character n-gram model. So it can infer a vector from all the n-grams of character n-grams within a word. If it hasn't seen a word enough to actually have the vector for it already in its vocabulary. So this is good when you need to deal with out-of-vocabulary terms. They are not as high quality as the words in your vocabulary, obviously, but it gives you something, and that's usually better than nothing. And then finally, for a lot of what we're doing, we need to actually know something about phrases rather than just words. For instance, we might want to know something about data science. And if you know the set of phrases, you have a closed set of phrases that you know you need to know something about, then a simple, cheap trick that you can do is just take all instances of a phrase, data science, that occur in your corpora, and replace the spaces with underscores, so that FastText will then tokenize this as a single word, and it'll infer a single word vector for you. So this is great if you need to know about cities in the world. Then you can just get a list of all the major cities in the world and be done. You can have it infer a single vector for New York rather than two vectors for New and York, which won't go together very well to give you New York City. But if you have a more open set of phrases that you might want to understand, and you might need to keep adding to them, then there are other techniques for figuring out either learning composition functions to put vectors together to get a new vector, and there's some references at the end of my slides, or to figure out which phrases you might want to segment together and give a non-compositional vector for. So at the end of the slides, you can see some references for how you might do that. And with that, I'll hand it off to Namrata.
Okay, thanks. Thank you, Adam. Okay, so now that we have some basic understanding of what word vectors are and the SkipGraham model of word vectors, I will talk about how we use the word vectors for improving search across Workday's products. And before we dive into the hows, let's talk about why is search so important. Well, search is at the core of most of Workday's products. And to give you an example, the talent product, right? It is used by recruiters for finding candidates to fill an open position. So a typical search query would be software engineer Java. And the expected search results is the resumes of candidates that are software engineers and have experience in Java. Another example of a product of our product where search is used extensively is the human capital management product. So consider an employer having its employees create their profile within Workday. And in their profile, they enter their names, job titles, and skills. So when they add skills to their profile, they search for skills such as Java, Scala, etc. And then the expected results are the skills that they search for, which they can select from the list of results and add to the profile. So having a clean list of entities, and by entities I mean job titles and skills, etc., in order to bring back relevant results, is really paramount for the success of Workday's products. Now, what do I mean by clean entities? There are a lot of different sources through which these structured fields such as job titles and skills, etc., get populated into the system. To give you an example, again, going back to the talent product, let's say a customer has been using the talent product and they use it for collecting resumes. And they have been using a resume parsing system one that extracts structured fields such as job titles from the resume and skills. So you can see here that the job title that was extracted contains unwanted text such as to the years of employment. And so does the skills. It contains programming languages and a comma-separated list of the skills. Let's say they move on to using another resume parser, which does slightly better job than the previous resume parser. And this time it does a good job at extracting job titles. But again, skills are extracted as comma-separated list of strings. And now let's say they move on to a much better refined resume parser. And this time, this resume parser does much better job of actually extracting the entities. So when these get populated into the system is now going to contain redundant occurrences of entities. So you can see that senior software engineer appears in line 1 and also in line 3. And there is unwanted text such as the years of employment or the programming languages, etc. So what we really want to do is clean up the data so that we can use the cleaned up entities for generating their word vectors. So we tried different approaches, starting with some simple regex-based approaches to clean the data that we had. The first approach we tried was partial match. So given a string that contains an unwanted text right here, database, the partial match approach will be basically just extracting the desired entity, in this case SQL, from the string. Next approach is multiple entities, another regex-based approach where given a comma-separated list of entities, you want to resolve it into individual entities. The third type of entity cleanup approach we applied was more for enhancing or improving the user experience. And by user experience, I mean, let's say the extracted entities were iOS and MongoDB. So when they are searched in the product, you want to show them in the right casing. So we want to resolve iOS to I capital OS and MongoDB to M capital and DB capital, right? So we looked at the capitalization frequencies across web crawl for some of these close set of entities and resolved them to the right casing. Yet another cleanup that we applied was synonyms canonicalization. So to give you an example, when somebody searches for, let's say a recruiter searches for a software developer or a software programmer, the expected search result should be similar and relevant to the search query. This is a much harder problem to solve, and we are currently working on it. So I'll talk about what we have done so far and what we are currently working on in for the synonyms canonicalization. All right, so once we have a set of cleaner set of entities, we generate word representations for them. We evaluated over 7 different data sources for generating these word representations. And the different evaluation techniques that we used were task-based. And I'll talk about those evaluation methods as I speak about the tasks that we evaluated them for. One thing that we did in addition is, given the phrases problem that Adam talked about, so given a phrase such as data and science, we rechunked the entity, the words in the entity into one single word. So data underscore science would be the word that you want to look up in the data source and generate a corpus of bag of sentences that contains those entities, right? So once the word representations are generated, we use them for improving the search. The first use case that I'm going to talk about is enabling broad search. Now, what do I mean by broad search? Consider an example, again, a talent or a recruiting example. Let's say the recruiter enters a query, software engineer, functional programming. So the expected search of the expected results that are returned will contain functional programming. But we went a step further and we wanted to show results that also contain entities that fall under functional programming. So for example, bring back results or resumes of candidates that have experience in Scala or Haskell or other functional programming languages. And we did this by building a hierarchy between the categories and the entity that fall under the category. And in order to build this hierarchy of the entities, we used word vectors. So the way we do it is, given a list of new entity that you want to find a relevant category for, you generate its word vector. And then you generate the word vectors of the categories in the hierarchy. And then you find the top k most similar categories to the entity that you want to add. And you use cosine similarity to find those top k similar categories. And then a human would go in and find the most appropriate entity that you want to add, category that you want to add this entity under. Another task where we used word vectors is clustering. So adding new entities, if they are in their own group, it is much faster to add to the hierarchy. And I'll explain with an example. So here to the left, we have a set of new entities. In this case, we are taking example of skills hierarchy. So what I have on the left is an alphabetically ordered list of skills that I want to add to the hierarchy that I have here on the right. So if you look here, since they are in alphabetical order, adding them will be a much time-consuming task. So the first thing we want to do is group them according to their similarity or relatedness, and that's where we use cosine similarity for clustering related entities together. So Adobe Photoshop, Affinity Photo, Pixel are all related skills, and SQL data warehousing, relational databases is another cluster of related skills. So now let's say you want to add Adobe Photoshop to this hierarchy. You generate its word vector, and you also generate word vectors of the entities or the categories in the existing hierarchy, and you find the top k, in this case, top 3 most similar categories. And then you choose the most relevant category that you want to add the entity under. So now what happens is when you search for photo editing software, the search results will bring back relevant documents containing photo editing software, but they will also bring back relevant documents that contain Adobe Photoshop. So that's how we implemented or broadened the search on some of the entities. Now, I talked about evaluating the word vectors that we generated based on the tasks that we were using them for. So here's how we went about evaluating the word vectors, the different data sources that we use for generating them based on the ingestion score. Now, to explain what this is, it is basically used to determine the quality of the category recommendation that is given by the word vectors, right? So consider an example. You have what we, in order to calculate the score or evaluate the model, what we did is we took an existing hierarchy. And we sampled a bunch of entities out of this hierarchy and consider that as the new set of entities that you want to add to the hierarchy. And now for each of these entities, generate their word vectors, find the top K recommended categories that you want to add it under. Now, if out of those top K recommendations, the categories that are recommended, if they are actually the parent or a sibling or a grandparent in the hierarchy where this entity was pulled out from, then we count that towards a success. And we calculate the ingestion score across all the entities that we sampled. And we saw that the data source that we ended up choosing for generating the word vectors gave us approximately 48.5% increase in the quality of its recommendations. The next use case is entities recommendation. Now, what I mean by entity recommendation, let me give you an example. I'll go back to the human capital management product example that I gave some time back. An employee creating their profile within Workday tries to add skills to their job profile. So let's say they enter a skill, Scala. A typical search result would be Scala and all other strings that contain Scala, right? We went a step further and we made our search results, or search rather, more intelligent in that instead of returning only Scala, we also return related skills, let's say, for example, Java, C#, VB.NET, etc. So now what happens is when the user gets these other entities that are related to the entity that they are searching for, they can select multiple skills at the same time and add to their profile without having to add or search them individually. And again, we use cosine similarity for grouping the related entities together. So here's an example. Let's say before the skills recommendation was implemented, if the user wanted to add MongoDB to their profile, they search for MongoDB and the search results contain different strings that contain MongoDB. Now, after skills recommendations, if they search for MongoDB, we return a list, an exact match of the skill that was found, along with related skills to what they were actually looking for. And now the user can just go ahead and select multiple skills that they know and add to their profile instead of having to search for them individually or type them individually into their profile. Now, again, going back to my comment that we evaluated our word representations on several tasks, and this is the second task on which we evaluated the performance of the word vectors or the quality of the recommendations that were made using those word vectors. And the technique that we used here is given a set of entities and their related set, we used their co-occurrence in the resume. So in this example, how many times did MongoDB and NoSQL occur together in the resume, and use that count across the list of entities to generate a score. And we saw that the data source that we ended up using for generating the word vectors gave us approximately 50% increase in the quality of the recommendations. And third and the last use case that I would like to talk about is synonyms. And like I said, synonyms is a much, much, much harder problem to solve. And we are, in fact, currently working on several other techniques to identify synonyms in a data set. Well, the use of synonyms here, as I mentioned earlier, is for disambiguation and query expansion. What I mean by query expansion is, again, going back to the technical recruiter example, right? If they're looking for a software programmer, it should bring back the same results as it would for a software developer. So here, software examiner and software programmer and a software developer are synonyms of each other. So we used fast-text subword model for generating the word representations. And the property of the subword model is that it is an n-gram, character n-gram model. And again, we used cosine similarity. But since this is a harder problem to solve, we also use some rule-based approaches for identifying or annotating synonyms. So one such rule was to see whether the words are similar in meaning. Another rule was looking for abbreviations. So here MS Excel is same as Microsoft Excel. Yet another approach is, or the rule is to see whether it contains the year or version and just extracting that out and resolving it to its canonical form. And lastly, spelling errors also are considered as synonyms. So synonyms is a hard problem. We are trying to add more signals to our synonyms detector. There is a more popular method in the literature using anchor links for finding synonyms. So that is something we are working on right now. Polysemy is yet another hard problem to solve, words having multiple meanings, and that is an ongoing work. Using SkipGrams is very expensive as far as phrase vectors are considered, and we are looking at compositional phrase vectors and document vectors for generating vectors, word vectors for phrases. So that's what we have been doing at Workday, and we are open to take questions now. Yes.
I mean, she was talking about the clustering of the words. So did you use word2vec or something and then use cosine similarity and then finally clustered? I mean, how exactly you approached it?
So the word vectors were generated using fast-text SkipGraham model. And we generated, yes, you're right, we generated their word vectors, used cosine similarity to find to cluster them together.
So you kind of say kind of cosine similarity between each and every pair of the words there, right? Or sorry.
Yes, do you?
I think we used either GenSim or some other off-the-shelf nearest neighbors to just find k nearest neighbors.
Yeah, we also use the k-means algorithm for clustering. Yeah. Yes.
Do you have your own custom algorithms or you use OpenNLP or Stanford for the processing, pre-processing and all you are saying, right?
For the pre-processing of the data, well, for now we use our in-house methods. Yeah.
A lot of it is open NLP stuff. I mean, most of what we have to do to make it work for our use case is train it on a corpus that's narrative vocabularies of interest that are pre-processed in a task-specific way. But many of the components are open.
Is there any specific reason you used fast text as a word vector instead of word to vector? So why you guys choose fast text? Is there any specific reason? I know we can use the word to vec to generate the word vectors. So, are there any differences or any challenges faced?
Do you want to answer that?
Sure. I haven't done a direct head-to-head comparison, but we have used both. We've used Word2Vec partly because it's parallelizable across boxes. And that's not a feature in FastText as of yet. FastText is very nice because it gives you vectors for out-of-vocabulary items in case, for some reason, in most of our use cases, we should get vectors for all of our vocabulary items because we can prune away and we often end up throwing away things that don't have enough mentions in our corpus in the first place because most of that is noise. But occasionally, something gets in and it's nice to not have it throw an error because it didn't have a vector. So that is one reason to prefer FastText.
Well, we use a lot of human annotated data for understanding the quality of the recommendations given by our representations. So the way we went about, one way was to tune the hyperparameters, and is there
Yeah,
anything else?
we also have, so we qualitatively looked through a lot of the vectors and suggestions to make sure that there's nothing really embarrassing going through some of them. So that was a concern. And for some of our models that were for similarity that are not based on word representations and that were trained on for certain corpuses, they actually gave some pretty not so helpful suggestions that we didn't really want. So that was part of the process, yes. The other part of the process is that we've released some of the results to partner clients, and they give us feedback too. And so there is definitely, like, in some cases, we're making suggestions that seem reasonable but are not actually helpful. For instance, like, a lot of musical instruments tend to be the same. So one of our clients wants someone who like knows violins doesn't necessarily want to add bassoons, like that they can play a bassoon onto their profile. So that's an example where it's not that helpful, and we would like to improve that. But that's just getting started. But we definitely do need this feedback. There's a fuzzier notion here of like false positive and false negative, because we do have some cases where we're using them as features for categorization, and then we have humans label them, and we iterate on the categorizer too. So does that answer your question? Okay. The SkipGraham for kinetic sampling is pretty general. As long as this substitutability is informative, like if the context of the words that appear in context in a corpus is informative, then that's probably going to be a useful signal, but in some tasks you might need different signals as well in addition.
Right. I would like to add to that. So it also depends on what corpus you use for training the vectors. So it is really more relevant to whatever use case you are trying to solve. So you can use SkipGraham, but it all boils down to what corpus you end up using for generating those vectors.
But yeah, it's very popular. Like the word vector technique is very popular for kind of transfer learning, because you can train up word vectors on a gigantic corpus of unlabeled data, and then you can use those as input features to some other task. And oftentimes it will do better than trying to just train on the small amount of labeled data for that task that you have.
So to identify the word pairs, like he has given the example of New York or something like that. So do you use any automated technique to identify such pair of words and then combine using that underscore in the middle? How did you approach that? Is that a manual?
Well, we did a brute force.
Yeah, in our cases, we just had a short list. In many of the cases, we have a short list of phrases that we care about. And so we just go over that short list and find all occurrences of it in the corpus. One of the references is a paper that gives you an automated way to try to infer when you don't know what phrases. So that would be, I believe it's number 2.
Yeah, it's the number 2.
Number 2 is the reference that you want there. That one will give you one example that that crew did to figure out which phrases are going to give you the most bang for your buck in terms of putting them together and inferring a non-compositional vector.
Last question from my side. So to identify that software engineer is synonymous to software developer or software programmer, for example. So once assuming that you identify those things, do you map that to a similar one, a unique one, something like, okay, so all software programmers map to software developers still map to software developers, something like that?
Yes.
How did you approach that? Because I'm dealing with similar problem actually at my work. So.
We can take that offline, but it's synonyms canonicalization that you're talking about, and finding a canonical for the words. Yeah. Okay, thank you everyone.